Hello, everyone. Welcome to the today's webinar with Oren. As part of the AI and Biotech Initiative, our initiative is partnership with Bits and Bio and Nucleate, and very excited to let you know more about AI in biotech. We have a series of programming as part of AI and biotech, including virtual panels, mentorship and coaching, in-person networking, as well as resource pages. If you're interested to learn more about AI in biotech and some of the programming that we have, you can check out our link tree or join our team. We can also post those in the messages as well, so you can have access. And also, if you're interested in partner or sponsor with us, please message us at ai.bio@nucleate.org. With that, we going through the talk today with Oren. I would like to welcome our speaker, Oren, a graduate PhD student from Oxford. He worked with NASA and is currently work with OpenAI preparedness team. He has done fantastic work on the frontier of LLM and biology, particularly the risks associated with large language models in the context of lab automation. Today's webinar format will be a half-an-hour presentation from Oren, followed by 30 minutes Q&A session with the audience and our team, Jacob and I. Make sure to post your questions in the chat and we'll go over them. It's a pleasure to have you, Oren. With that, I let Oren to introduce himself and begin his talk. Thank you.
Well, thank you, team. It's a pleasure to be here. Right, my monitor is going to be going here. I'm going to be staring slightly into the distance for some of this talk, but I am paying attention. Promise that. Right, let's jump in. Let me just make sure I can share my screen, okay? Can everyone see my screen okay? Are there any issues? I mean, that's right. Let's jump in. Thanks for coming, everyone. I'm Odhran, and I'm going to be talking a little bit about AI-driven lab automation. I'll talk a little bit first about why I think I'm qualified to talk about this. So I previously did medical sciences, then a PhD in machine learning at Oxford, and that formed a lot of my background work, which was mostly in the medical and biomedical settings. From there, I worked with Sam Rodriguez, leading a team within his team, working on AI methods for writing biological protocols. And this is where a lot of my work on ideas around AI-driven lab automation have come from. After that, I've been contracting with OpenAI, and in that role, I focus on AI for pandemic preparedness, natural sciences, and global health. But in part of my wider thinking outside of this role, I continue to think and work with various different people in the lab automation space about this idea of AI-driven lab automation. Now, you've probably heard from previous talks over the past few weeks all the different ways in which AI may impact natural sciences and biology. I'm very interested to talk around where this may happen in lab automation, but I also wanted to give this talk partly from a lens of safety. Whenever we are developing new technologies, it's always worth also understanding what potential risks might be involved in that. And as scientists, we have a responsibility to make sure we all mitigate these risks together. So that forms the brief of why I'm having this talk, why I wanted to give this talk, and also why this hopefully may be useful to you all going forward into the future. So let's go on. Caveats about this talk. I'm giving this talk in my personal capacity. This talk discusses possible futures. Predicting the future is always hard. There may, of course, be predictions which do not come to pass. However, there's a lot of stuff which talks about the near future, and there's stuff that talks about mitigations that we should think about regardless of what the future may involve. So my hope is that we will all learn something from this talk. So let's get on with the actual content of this talk. Lab automation. Why should you care? Where we have working lab automation, we can do some pretty amazing things. The idea of lab automation is that we fully automate science. This means we can do a lot more science, which is very valuable. But there's more nuance to it than that. Firstly, there's this idea of higher throughput. Like, we can do experiments where we can have hundreds of different possible combinations that normally as humans we just wouldn't bother doing because it's too much work on the graduate student staying up until 2 a.m. On top of that, we don't need the graduate student staying up until 2 a.m. Like, having work that can be done 24/7 is really useful. It also allows us to do certain experiments that, like, by their very nature, require constant supervision. Examples might be things like directed evolution. On top of that, one thing that's really interesting about having experiments run by robots is that, in theory, we log everything. All those little things you forget in the protocol, like what the temperature is, what the atmospheric pressure is, what the humidity is, what time of day it was, these things ultimately can affect the actual experimental results. We do that on a computer, we do that with robots, we can log everything. Similarly, we have all those results logged, including the things that went wrong. This is really informative in theory for allowing us to iterate better and better at doing science. Of course, if we're doing this all in one place with like one big automation facility, we also get the advantages of having all this data in the same format, all of these experiments running on the same machines. We, in theory, get some ability to learn more from that. Similarly, if kit is standardized for automation, there's potentially advantages for reproducibility. That's maybe a little more. Now, can you see my slides?
Now it's awesome. Yeah, all good.
Brilliant. Okay, phenomenal. Yeah, I'm so sorry about this, everyone. That is not the norm, but we're all still here. Anyways, let's keep going. Lab automation, what is it? Hope you can hear me clearly now. We've had lab automation arguably since the 80s. People have got liquid handling robots moving liquids around. This works great for things like high throughput screening. If you want to, screen a substance against like 2,000 little drugs, you can do this. Pharma's been doing it for years. There's no real issue with it. The issue is in the interface with humans. Ultimately, humans are loading these things. They're taking the samples out. In some cases, they're also reading the results. So the actual capacity for full automation isn't really realized by these pieces of technology. So what's changing? In the last few years, we have seen startups begin to adopt these ideas of trying to integrate different bits of the lab together. There are things like automata, that's one example, Emerald Cloud Labs, which I'll come back to in more depth later. But all these companies are trying to do is they're trying to say, okay, this thing is automatic, this thing's not automatic, another thing is automatic. We can kind of glue these things together. This is a good example here. This is an automated system running a plate reader between different other devices and a liquid handler. The main thing to note here, of course, is that this isn't everything in a lab. Like, you'll notice there's no fridge. You'll notice there isn't a centrifuge really connected. Like, there are other key bits of lab equipment which aren't necessarily integrated with this sort of stack yet. And on top of that, these are often built for custom jobs, like a specific function in a lab. So while we're getting there in this capacity, it's not everything. However, people are trying to push the envelope and are trying to automate as much as they can, and making this available then to as many people as possible. An interesting example of this is the idea of cloud labs. These are a very novel thing. Emerald Cloud Labs is probably the furthest ahead. A few others are sort of beginning to take root. But the main idea here is that you try and automate everything and then make this automated lab available on the cloud to anyone who wants to use it. This is a very noble undertaking in terms of trying to get this all done. And one of the arguments of the advantage of this, right, is that if all this data is centralized, you may learn how to do this better over time. So as part of this, people are also developing scripting languages, ways of describing all of the actions in a lab. Don't worry about reading the stuff on the left, but just know that like we are beginning to think about like how we program science. We have like rough forms of this, things like Opentrons, a liquid handler has like an API in Python. We have sort of comprehensive forms of this. ECL is an example of this. But there are, of course, still barriers. There's a reason we aren't all running automated labs right now. Let's talk about these barriers. Firstly, there isn't really the immediate financial pressure from any scientific manufacturer to make their device automatable. Let's take like a scientific fridge that needs to go down to like minus 50 degrees. That is a very high margin, very lucrative business. You don't need to make an automated fridge to be a good scientific fridge company. So there's not really a consideration of like how these things might be automated. And so there isn't a consideration of like, well, how can a robot open a fridge? On top of that, there isn't really centralized provision in science. All our different devices come from very different people. Some can be very niche. And even if devices are designed to be automated, there isn't immediately a way of integrating them together. It's not like you have like, I don't know, a car where all the parts slotted together perfectly. This is a lab. The devices are fluid. You don't have that ability to just glue things together and have them magically work like Lego. Another thing, of course, is cost. Like a lot of lab automation equipment is expensive. An Opentrons itself is around $15,000. based on the science you want to do, that may be a drop in the ocean, but for other scientists, if you're trying to automate the whole lab, that's a very big investment, especially if you're doing just one type of experiment, which you may only be doing for a few months as part of iterative testing in a PhD. Finally, and I think most notably, there are difficulties in programming robotics. When you have to control every single component of an experiment, humans aren't really used to thinking in that way. And it's one of the reasons we have a lot of errors in science, but it's one of the reasons we can, have serendipity and do this sort of discovery. Writing scripts for robots to do science is a hard task. So let's talk about AI-driven lab automation. What might the AI be used for? Generating protocols and writing scripts. This is probably the lowest hanging fruit. We can get AI to help us write how to do science. Debugging and improving experiments. We can get AI to look at what we've done and what's gone wrong and say, hey, can this thing be changed? Have you tried this thing instead? And critically, we can also get it to actually run the robotic connections. Like, it's one thing to have these automated devices. It's another thing to glue them together. General purpose robotics facilitated through AI can probably help us glue some of these bits together. So let's talk a little bit around the protocol task. So is AI good at writing protocols? It is. This is the work I focused on and also did a bit with Jakob himself, who's also in this call. But this work addresses the idea of getting AI to write long protocols for biology. We found that if you get AI to write pseudocode and use functions, you can get AI to write pretty long things because functions are little blocks. You can do all these advanced techniques in AI, things like retrieval augmented generation, where you take information from the past and reuse it to generate things going forward. You can use ways of combining new functions, building new functions, all these fancy things. And you can take all that the models learned about writing functions in the past from reading tons of Python and use this to get models that, in theory, can generate pretty good long-term plans for experiments. When we did this work, we were able to find that we could get multi-step experiments. This was a one for doing an overnight culture and cryopreservation of E. coli and glycerol for long-term storage, an entirely AI-generated protocol that works, and it probably had about 40 steps in it. So we have faith that these models right now can be used to help people design experiments. Similarly, right now, models are being used to write scripts. Opentrons has an open project getting LLMs to write their lab automation scripts. There's a few academics that are working on this as well. We've seen Gabe Gomez in CMU having ideas around this. The Emerald Cloud Labs teams themselves are also working on this. You also see this being done in chemistry, most notably perhaps with the Matter Lab in Toronto. But AI is getting pretty good at writing protocols and just writing the underlying code for lab automation. We're also doing quite active research in this area. People are doing things like iterative feedback. I mentioned the Matter Lab before. This is another example of research that they're doing right now, where they are defining a pseudo language for describing all of chemistry and getting robots to write in the pseudo language. Whenever it makes an error, you can kind of see ideas of errors and feedback. It may make an error. A system can say, hey, this doesn't look like the right scripting language. Let's fix this. And this iterative feedback can allow for a pretty accurate generation of long-term tasks in writing protocols and running experiments. And in this case, the Matter Lab is getting this running on robots. Finally, you've probably seen very recently all these little things going on with general purpose robotics. We've seen many tech demos from different companies showing what these things can do. Of course, this stuff's still on the cusp of what's possible right now, but this can be used for biology as well. There are companies like Medra, which are very interested in this idea of using general purpose robotics to run scientific experiments. And where they really help with is in integrating different bits of the kit. They may not be able to do everything, but they can help a lot with wider coverage of automation. Is everything clear so far? And does anyone have any questions right now? I'm going to take that as a yes, but feel free to drop any questions in the chat as we're going. So let's keep moving. Why are all labs not being run by robots right now? Firstly, we're not 100% there yet with protocol and code generation. We're getting pretty good, but we're not going to do everything perfectly. Secondly, there are still issues with debugging and feedback on physical systems. It's one thing to ask a GPT model, hey, my experiment didn't work. Why might it be? You may get some pretty good advice on that. It's another thing to have a robot do something and then work out why the robot went wrong. This requires things like visual feedback, feedback from the underlying motor commands, a good way of expressing that in a way that an AI can understand. Like this is still something which is being actively worked on. There are, as I also mentioned, significant hardware costs. General purpose lab automation devices are expensive. So is general purpose robotics. We're a long way from having a general purpose robot in every house. We mentioned this idea that like we need general purpose robotics to integrate different devices. We're still seeing how viable that is. And perhaps most importantly for science, there are issues with dexterity. Some tasks in science are very precise. You may be working with a micropipette, you may be inserting patch clamps on neurons. Like, obviously, there are some ways you can think about automating these techniques. But if you're doing something novel and on the fly, which may be the first time anyone's done it, you may not have a good way of automating it. And having a robot with like very coarse grained actions will probably destroy whatever device you're trying to work with. So, with all these things being said, we still need, as part of this talk, to give an idea of what may happen in the near future. That's my goal, right? Give you a prediction. So, what might be the next steps? Where might the future go? So here's probably what won't happen. It's unlikely that we are going to see like lots of custom built lab automation devices, I think. There isn't really the financial incentive for this to happen. And as nice as it might be to have all these different like lab automation devices, we've seen a lot of companies try to build full stack lab automation things over the last few years. And none of them have taken off in the way they're perhaps hoping to. I mean, that's maybe unfair. Like, as I said, this is a future prediction. This is my prediction. I may be wrong. But like my 2 cents is that we are not likely to see like full suites of like custom built lab automation technologies. Similarly, the data that might help us kind of train better models, i.e. having a massive data set of like protocols for experiments and for lab automation, is probably unlikely to arise in the open source. We've seen like things like protocols.io exist, which is meant to be this big database of like protocols that everyone's using. It's got like 40,000 protocols in it, and some of them are things like baking cookies. Like this is not necessarily high quality data. And there, again, isn't really the incentive for this high quality data to exist and materialize into the public domain. So unless incentives radically change, I think it's unlikely that these things will pass. However, there are other things that could pass, and I believe these are potentially more probable. Firstly, general purpose robotics improves and becomes more affordable. There's a lot of push right now from a lot of different people to make this a new technology. And if this technology works, it stands to reason we can use it for science as well. There's also the fact that general purpose language models are getting better and better. So even if we don't have a custom data set just for protocols in like a nice format for doing very specific protocol-y things, it stands to reason that the models will ingest enough scientific data to give good suggestions for protocols and good ways of feeding back on them, just because there will be some protocols at least in their data set. Thirdly, I expect iterative feedback will improve. We already see we can get iterative feedback from language models on designing protocols through text. A big part of science is visual understanding, like looking at a cell dish and saying, hey, these cells are dead. Why is that? What's happened here? Like that visual feedback is going to be another thing which significantly improves performance. And finally, on this idea of collecting data, when we do see cloud labs begin to take off, and when we do see automation providers begin to take off, they are going to be the people that collect the most data on running experiments in one standardized format for training. So we expect there to be advantages in scale, where a few companies may succeed, and then these ones will have the in-house expertise to understand how to automate experiments effectively because they will have done it so many times through machine learning in their own custom data set. So that's kind of my model for like what may happen. So let's talk about like the near-term future. Partial automation. Automation is unlikely to come all at once. Different things are automatable to different degrees. We will probably see, well, actually, right now, we already see protocol generation. We do have the technology in theory for visual AI feedback on experiments. Like this idea of like automation is a very weak one, but it is one which is possible right now. Like we can have AI help us design experiments and help us give feedback on it. We're still a massive human in the loop, but like that's kind of there. Probably the next biggest low-hanging fruit is successful use of general purpose robotics to integrate different lab devices. These are the coarse-grained ones, things like your liquid handlers, your plate readers, maybe even your fridges if you're lucky. But like things which like don't require high dexterity movements, like this is kind of like the next step of automation, and hopefully we can move more and more things into this automated paradigm. Ultimately, it's likely that a lot of high dexterity tasks are still going to take a long time to automate because the underlying hardware for high level precision isn't really there yet for current robotics. And no doubt the first wave of mass manufactured robotics for robotic automation isn't going to have this fine level of dexterity as a primary consideration, because for most manual tasks, you don't need that. So that gives a summary of the sort of model of the possible future for lab automation. That's my when might it happen part of the talk. Now I need to have the serious conversation of what are the risks? What are the risks? Let's go. So let's talk about large language models and tacit knowledge. Previously, academia and study has been a gatekeeper to biological knowledge, which in some ways is a bad thing. Like it's good for people to know more about their health and know more about the nature of the world. In some ways, it's a good thing because it can prevent people who may be dangerous getting access to this information. Large language models have changed that a lot. They have made information a lot more accessible for a lot more people. Now, obviously, there's a lot of safety consideration that goes into how we mitigate the risks of this information existing, but there are, of course, still risks with any new model coming out, particularly open source models that may not be safety checked, around the information that people eventually get access to through this kind of model. This is one thing which like creates risk. And we have this the idea of large language models without biological design tools. Then let's next talk about biological design tools. So at the same time that language models are advancing, there are also a lot of other tools for machine learning in biology that are advancing very rapidly too. You've probably heard about them in other talks that have been given over the past few weeks. These include things like AlphaFold for predicting protein folding. These include things like RF diffusion for generating protein backbones. These include a host of other models for predicting genomic interactions. These include foundation models that just read nucleic acid sequences. Like these models can allow us to design new biological molecules, and they're very powerful in themselves. We call these biological design tools or BDTs. And the thing that's interesting about these is these create new risks when used with large language models. You know, if you have biological design tools and if you have large language models that can use biological design tools, you as a non-expert in theory can ask a model to design something pretty wild, and you might get a protein that does the right job. Now, lab automation really builds on these risks from AI and biological design tools. You have the same things with like large language models where there's less expertise requirements, and you don't necessarily need to learn like, you know, things about biology. With lab automation, you may also not need to learn any manual skills for actually doing the underlying wet work of pipetting and putting things in fridges and centrifuging and incubating and all these kind of things. On top of that, there's a lot of this idea of like tacit knowledge. This is knowledge which isn't necessarily written down in a textbook, but may exist in other forms on forum posts or just in conversations and in videos. If large language models have greater access to this tacit knowledge may be the key requirement for really understanding how to build experiments. And if your model can integrate this tacit knowledge into running experiments without you even in the loop, that potentially allows a lot more people to build things without prior understanding. Finally, if cloud labs become what they're envisioning to be, which is like a way of democratizing science by creating these cloud labs that you can use anywhere, that in theory removes some of the barriers of cost and reagent access. If you can get into a cloud lab, they may have compounds you can't find elsewhere. They may significantly reduce the cost of you otherwise setting up your own lab. This also creates a risk of access. So that sets some of the risk of access side. There's also just some underlying risks with biology as well. When you have lab automation, it's easier to work with hazardous substances. Like you can work with a gas that would be toxic to humans. Chemical risk becomes, like, in theory, easier to carry out. There are also experiments which are allowing new risks to be created that are better suited to lab automation. Examples of things like directed evolution, where you might iteratively evolve bacteria or viruses against some sort of target, and this requires constant monitoring, constant checking, constant feedback. If you can have a robot do that 24/7, that's a very useful thing to do for these sort of risk models. So what can we do about these risks? there is a lot going on right now when people thinking about risks in biology. There is an executive order right now from the White House discussing some of these possible risks in AI models. There are lots of different biosecurity groups that work on this across the world. However, lab automation is maybe a little neglected area just because it's not the current reality. Luckily, a lot of the approaches that people are using in other fields are directly relevant to lab automation there. So it's worth talking a little bit about these. Firstly, I mentioned that lab automation kind of follows on from biological design tools. Don't worry about reading all of this. I'm just putting up here to show people that people are thinking about this in quite a degree of depth. This paper, Towards Responsible Government of Biological Design Tools, Boulange et al. In 2023, I think is a great one. It gives an overview of a lot of different methods that people are considering for mitigating possible risks in these systems. And I'll talk about a few of these risks in more depth. We've got model evaluations, we've got structured access, and know your customer, these kind of really overlap. We've got nucleic acid sequencing, and we've got securing lab equipment. Let's talk about these in a bit more depth. So, on model evaluation, as I mentioned, there's currently an executive order right now to require all companies developing dual-use foundation models to submit regular reports to the government, including efforts to safeguard model weights and to safety test models via red teaming. This is a process where engineers will intentionally try and break models or discover security flaws or potential capabilities that are unexpected so that these risks can be mitigated. And I've also shown this diagram below. This is from Epoch. They're doing great research on this wider space. But this shows the way in which the US is currently thinking about dual use. They don't have a good definition for a dual use model right now, and they're still working on what this might be. So currently, the only definition they're using is like if a model is big enough, in this case, a computing power greater than 10 to the 26 integer floating point operations, then we will flag it as a potential risk. Like this is a good example of like the fact that we are still really in flux about deciding where we need to start considering risks, because our models right now are like having their parameter counts shortened by their architectures underlying changing. But this safety testing is really important. It needs to be done. And in the same way it's being done for models to design proteins, it should really be done for models that run lab automation equipment too. Next, DNA screening. This is being done very broadly by lots of different groups. I've drawn attention to Secure DNA, a group at MIT that does this sort of work. But for most biological risk, at the very least, just putting chemical risk on the shelf for now, DNA is the key ingredient. Like if you want to build something that's dangerous, you want to get smallpox out, you want to get an influenza, like you're going to need DNA at some point. And that DNA is going to look, for the most part, like smallpox or influenza. So a lot of work's being carried out to like require all DNA sequences to be screened before they're used. If you are a lab automation company, you need to make sure your DNA sequences are being screened as part of the production. On top of that, like one of the nice things about lab automation as a technology is you have the option to seamlessly integrate DNA sequencing. Because even if you like sequence initial DNA, an experiment might involve things that change DNA. It might involve two strands together. It might knock things out of the DNA strand. It might turn it into a risk without it initially being a risk when it started. So lab automation in theory lets you do more repeated sampling of your underlying like experiments that are going on to check if risks aren't being created on the fly. So this is a natural advantage to lab automation for getting better coverage of possible risks being created. This, however, is all being said in the context of DNA sequencing availability. If DNA sequencing and DNA generation becomes easier to do just in your shed, this whole model it becomes a little shakier. Doesn't mean that we shouldn't consider it as a major way of like preventing threats right now. Finally, know your customer checks. Not finally, but another option. We need to think very carefully as an industry around like who we give access for these models to. Ultimately, I think a lot of biology and a lot of science is very much like pro openness. There is a lot of advantages to that. We want science to be shared as widely as possible. We want to see the benefits realized for so many people. And there's a lot of people that can use our models who otherwise wouldn't, who get to see the benefit of that. However, there's a lot of risk to be thought about in here as well. With something like know your customer checks, we may say, hey, we're not going to give this lab automation model to anyone who is an academic or anyone who hasn't gone through a certain degree of security clearance. Like these are real considerations we need to make as a field. Finally, something which I think is under investigated is the idea of AI as a defensive technology. We talk a lot in biosecurity around these ideas of the risks AI create and possible mitigations. But ultimately, like AI itself can be used to try and identify possible risks and identify possible mitigations. A lot of the things we do for red teaming are around safety testing models, trying to spot possible holes in them. Red teaming, before it existed in the context of models, existed in the context of things like cybersecurity, trying to test and probe defenses. You can, in theory, use an AI model to try and work out if a DNA sequencing company has any vulnerabilities, or work out if a cloud lab provider has any vulnerabilities. These are very useful and scalable ways of like trying to plug vulnerabilities as early as possible. Of course, this being said, these technologies in themselves are very dangerous. If I'm building this suite of technologies that are designed to like try and get around the security checks in a DNA synthesis company, that is something which could be very easily repurposed into something which could be weaponized or used for danger. And so a lot of thought also needs to go into how you secure these mechanisms which are meant to be used for safety testing as well. So that has given a real overview of the possible risks, possible mitigations, and possible futures of lab automation. I want to go now onto some very quick concluding remarks. Firstly, AI assisted science is here. You can use GPT to help you write experiments. Secondly, partial lab automation is coming. We have, in theory, all the technology there. There are enough of like the components together, and particularly if general purpose robotics starts working, we can glue a lot of things together. Full lab automation, we have these very precise, minute actions, or working with like entirely little things that haven't been done before as new methods. It's probably further away. AI-driven lab automation is a dualist technology. It has a capacity to bring a lot of benefits to society. It also carries risks. And finally, defense and security is the responsibility of every biologist. We don't necessarily have all the answers yet, but we need everyone to think about how we make these technologies more safe and more secure. So that brings me to the end of the presentation. Any questions?
Thank you so much for your presentation, and please feel free to ask your question in the chat. And I did have one question myself. I'm wondering if there should be any ban on like open source service provider, and if there is like any like current kind of approach that is happening in that regard. Like for example, like people that are like hosting models, or what do you think it should be in terms of those organizations that providing open source software tools or models?
Yeah, this is a really interesting one. I think, this really shows a lot of people's personal preference or like personal ideals. I try to be, I guess, what I'd call a radical pessimist. The way I think about it is like if I'm a pessimist and I'm wrong about it, okay, maybe science doesn't move as fast. If I'm a pessimist and I'm right about it, everyone dies. That's maybe like an extreme, but in the context of biology and bioweapons, biology and biological threats can kill millions. So like I do think that like a lot more consideration needs to go into like how we secure models and model weights. Because even when we release open source models in biology, the people say, oh, this model's fine-tuned, or oh, this model wasn't trained on any dangerous data. Well, it's very easy to reverse fine-tuning. It's also very easy to like take a model that was trained on like sequences that weren't humans and then just give it a little bit of a top up on human data. Like if you release an open source model and you release the weights, even if you've done some sort of safety checks part of that process, there are steps to get around that. Now, of course, not everyone has the expertise to do that, but in the same way that like a GPT model democratizes expertise to biology, it democratizes expertise to fine-tuning a large language model. These are risks. So I think I think a lot more thought needs to go into particularly KYC controls around access to new models in biology.
And I'm also curious, how do you think about international collaboration over some of those issues? Because also that is going to be a big problem, especially as we go more with advances of like large language models and AI race.
Yeah, this is a thorny one. This is an interesting one. I think everyone is beginning to kind of wake up to like how big of a risk this might be. But what I would say is like from my perception, the US is the furthest ahead on this, and the country that's thinking about this most. Certainly, like no one else has really sent an executive order saying we want to audit all of your biological models. And not all of them, but the big ones right now. International collaboration is really important. We need to think about like what institutions are most appropriate for this. Things are cropping up like Secure DNA, I mentioned. That's a nonprofit started by Kevin Esvelt based in Switzerland, and it's kind of set up to allow for some of this like more international collaboration in the context of DNA screening synthesis. Sorry, DNA sequence synthesis screening. Get the right order of words. We need more things like this for biology more broadly.
Sounds good. We have a question in the chat. Maybe we can go over through that.
Yeah, I'm just reading this question. I just read out. This is from Austin Tripp. I just finished my PhD about algorithms for designing experiments for automated labs. If I'm concerned about the safety of these devices, where might I work after my PhD? Oh, I'm glad you asked that. We now have the AI Safety Institute in London. These people are, I think, doing some really brilliant work, and they have a chemistry and biology team, which is being led by, in part, by Jonas Sambrink, who was an academic at Oxford, who I also worked with previously. I think he's brilliant. I think they're doing very good things. I think they are very poised to think about this sort of safety testing. So yeah, the AI Safety Institute in London, working with the British government, and that's with Jonas Sambrink. That would be the first thing that comes to mind. There are, of course, other things, such as the Center for Long-Term Resilience, like things materialize, but like I think that's the hot thing right now. The fact that governments are waking up to this and are putting energy behind it, they need people. They need good people.
Excellent. One more question in the chat.
Maybe I can have a question
Of course.
as we're on the practical side of things. So I wonder, like, because we aim this initiative to be targeted towards startups or like people trying to think of starting a company. So what would be like your like a general framework approach that you would use were you to start a company, and you would have to decide, oh, should I be doing the experiments manually? Should I put in the resources to actually automate stuff? Should I try to use Emerald Cloud Labs, or is that like still so far away from like being like useful? I mean, it's difficult to answer that, right? Like specifically, but what would be your general framework to that?
Yeah, let's talk about this in more depth. So let's talk about like the state of the art of something like Emerald Cloud Labs, right? Emerald Cloud Labs, you cannot run biological experiments on it. They've had a coming soon section for biological experiments for about a year and a half. Like they haven't got biology experiments working right yet. Maybe that's a safety thing, maybe that's a practical implementation thing, but like that's the reality of ECL. I'll also kind of say, like, ECL as a scripting language does not come very naturally to me. It's not very widely used. It doesn't look like Python. It's all these things to it. Like it's, currently my personal advice would be like, look at all the other options as well when you're thinking about running an experiment. However, when you are thinking about things like future capabilities, it is really worth thinking about like automation and light automation first. Like having interfaces with GPT models to spot bugs in your protocols, get visual feedback on like, hey, why do my cells look like this? Like you can try this right here, right now, and you can see if this works. And I think this kind of gives you a taster of like, is this idea of partial automation going to be useful for us? Like, does this mean we get those benefits? Because ultimately, it's unlikely that the robots that drive or AI systems that drive lab experiments are going to be better than what you get from language models in natural text. They're probably going to be the same. And so if you get advantage from like natural text models and vision models, you may also get advantage from like lab automation. But you can discover that without having to invest hundreds of £1,000s in a lab automation stack that's driven by AI. That was one part of your question. Jakub, you asked me a second part, which I've slipped on. I guess like frameworks that startups need to use. I think the only other thing I talk about as a framework is this idea of like of risk and release. A lot of companies do release things publicly. And they say, oh, we safety tested this. Oh, we fine-tuned this. Oh, we didn't train this on certain data. Do think beyond that. Like it's one thing to have these mitigations in place. It's another thing to like be more systemic with like considering how people might use your mitigated technology and repurpose it. That's the one thing I ask startups to consider more than anything else.
I also had other question like related to small models. There's a lot of like at least in the context of like machine learning specifically, people like show like some performances comparable with like large language models if they're being like fine-tuned properly. And I'm just wondering like with the US like current framework that you mentioned, they kind of like ban like large language models, but like consider like they don't consider the risk of like a small models. I'm just like wondering what your perspective on that would be.
Yeah. My perspective on that is this is just sorry. Can you guys still hear me? Okay, I've just got a connection as unstable flag and it set off my fight or flight response. Okay, glad you can still hear me. So my perspective on this is that it's that way because it's early days. In the executive report itself, it says that they're still working on the definition of what dual use is. So they basically just use this like very high flop count as sort of like a first past the post definition of okay, well, like we'll try and use this and see if this catches some big things. A perfect example, right? Where like I think this is already becoming very rapidly out of date. You know, this idea of like limiting us to like a certain number of like teraflops of like size was really based around the understanding that like models are going to be transformer models, which is a specific type of machine learning. However, we're seeing in biology right now that some people are exploring alternative architectures that might scale better. And these alternative architectures have a lot less parameters. So even the idea of like a small model isn't relevant in the same way, because like a large model might also be significantly below this parameter count that the US government is looking for. So all I'll say is that like watch this space. The US may change its stance on like what it chooses to regulate in the near future, and it has said that it's looking to change its definition of what a dual use model is. So yeah, that's the best summary of that. I can see we've got another question in the chat from Austin Tripp around chemistry risk. Why don't I answer this one? So a lot of the talk is focused on biology. Do you think the risks from chemistry are distinct? My impression is that risks from small molecules are smaller, mainly because there are fewer small molecules, and bad actors might be less incentivized to design new molecules since they have plenty of net toxic molecules, et cetera, et cetera. I think you're right that they're distinct. There's a question of like, in what ways they're different. With a biological risk, obviously you have the risk of scale. Like you can infect one person, then infects more people, that grows, right? But you know, chemical weapons can be incredibly dangerous in themselves. They can maybe be cheaper to synthesize. They can maybe be easier to synthesize if you can get them from like common underlying chemicals. The same principles apply. Like you need controlled material access, and you need to be able to like identify when things are being created. You need automated red teaming, but like the risks are different. However, like there are still risks, right? You know, there may be threat actors who like a biological threat looks very different from a chemical threat. Like if a chemical threat is being used, it's probably being used in a more targeted way. And there are still risks significantly from AI, even making it easier to like access chemicals and bypass checks. And there may be, oh God, there are other risks which I think are worth talking about. I think that's a perfect example of something which like is probably best left to like a report for, God, I think there are other risks is the best way I'll say it. I think some risks in themselves confirm informational hazard, where it's not even worth talking about them unless you're really certain you want to talk about those in a public space. But yeah, I think there are real risks from chemicals. I just think the risks are distinct from biological risk. And given Nucleate is principally like biology, I wanted to talk mostly about the biological risks here. So that was a long-winded answer, but I hope that gives a good summary.
Yeah, I have another question which sort of expands on a completely different side of this of your talk, and that's about the like protocols and having a large data set of protocols. And so I wonder, like there's protocols IO, which is not really a high quality data set.
I mean, that's
so I
not
wonder,
really them, right? They're an open source data set for anyone to upload science. Of course, someone's
yeah,
going to upload how do I bake cookies into a protocols data set. That, you know, it's
right.
like it's like saying YouTube isn't a high quality science data set. It's got the same level of admin control.
Yeah, right. Yeah. So I wonder, like, do you think that there is it would be useful in a sort of step change manner to have such like have a probably like more widely accessible large collection of high quality protocols, or is that not really the way to think about protocol generation with LLMs? And if that would be very useful, like what sort of regime would you envision this to be? Like would there be like some sort of a protocol, like I don't know, like you would have to like there would be like some clear structure of what a protocol should look like, similar to like email or something like that, or it would have to be a concentrated effort of a single company, or what do you think?
This is a really interesting one because in some ways I think a good protocol doesn't exist. And let's talk about why. Like let's take the process of like like doing a DNA polymerase reaction. You could write that as like one step in the protocol. You could write it as like 50. Like you can have very varying levels of granularity in different protocols, and that might depend on how the protocol is written. On top of that, humans are really bad about thinking about every single control in an experiment. Like you are not going to perfectly control every step. You're going to miss things. Like one of my favorite things to do right now is like take nature protocols, which the best of the best, run them through an LLM and say, hey, what's this missing? And it pulls up like this like there are 26 things in here that have not been controlled. This will go wrong. So like the idea of like a good protocol data set right now is kind of hard to think about, but there is something around like data standards, because if you do find a way of like writing protocols, one thing that might be useful is like writing them as close as possible to code that can be automated. Because in theory, you're trying to like, if you're building that in a framework that is designed to like run on a robot, that by definition has to be like more controlled, and it has to be like more integrated into like repeatable stuff. But B, it does in theory allow for like easier communication of like these different primitives. There are people that are thinking about this. I am one of them. But like there is still like a lot of work to be done as around like what might be the most useful framework, because you want to make something which isn't overly restrictive, doesn't result in like a huge amount of overhead for scientists. They still want to use it, but it does allow for like clearer reporting, easier ways to spot like things that aren't controlled, and in theory, easier integration into like robotic systems if you wanted to do that down the line.
Excellent. I have another question for you as well. I think that there is a lot of like ideas around securing DNA synthesis, like especially like bringing all those providers together to make sure that they don't release, or like sequencing companies as well don't release like hazardous or dangerous or sequences. I'm wondering what step in the whole process of when using large language model should we have like safety guard? And what I mean here specifically, like for example, they like ChatGPT or like a future LLM models could tell you exactly how to build a synthesis device. So you don't need to have existing like companies, even you like work with them like truly, and they have safety guard. Like you can create those like at like either like some sort of a capacity there at the different institutions that is not regulated, or at like your lab at home or something. So I'm just like wondering, what do you think it should be done to prevent downstream effects of like some of those technologies?
Yeah, it's you kind of need to put it in as many places as possible, right? Where the defense is not a single wall, it's multi-layered. Ultimately, it's easier to have more and more defense closer to the source, right? As I mentioned before, like, if someone has the weights to a model, well, functionally, that's anyone can do anything they want with that. Like, that's just that cat's out of the bag for that one. So like, there is a significant role of government in like working out how we regulate this. There's a significant role of the labs that produce these technologies and working out how we regulate this. But beyond that, there is a responsibility of every lab that uses them to like say, okay, well, who's using this? Who in my lab is like making use of these models? Because like I think one thing which isn't really factored into like a lot of, well, it is factored into threat models, but like I think a lot of our threat model for like risk and models is like, oh, we will rely on like stewards, the government, big companies to kind of like protect us from the potential risks from these models. Risks can emerge from inside these companies. Someone can slip in, despite our best mechanisms as humans, someone may be a threat actor. They may become a threat actor. People can, we have seen people who have become unwell and then have become threat actors through that, through any sort of like condition that may involve their mental stability. Like, you know, we have issues with threat actors emerging, and that becomes the idea of like, well, it's everyone's responsibility to try and prevent these risks.
Thank you.
I can see I was just asked a to bring up a little overview of like the lab automation space. I do have one I think is really good. I don't have it immediately to hand. It's on there's a great one done by, I think it's Natalie, is it Nelly Tian? I'm trying to think. In the Bits and Bio community Slack. I will try and bring that up, and maybe I can attach that to like some email response to this talk if people wanted to see it. But yeah, I think that's answering that final question.
We also have a resource page as well we put together for CRN automation. The link is in the link tree. Make sure you check that as well. There is definitely some resources there. And we include some of the references that Odhran mentioned during his talk today as well in that list. Thank you. Jakob, do you have any final question?
No, I think I'm all good. I think I learned a lot today. We got one more. From Austin. Where do you plan to work next, Oren? What's on the radar?
Watch this space. I wish I could comment more. Yeah, watch this space. Right.
Ooh.
That's awesome. Well, with that, thank you everyone, and thank you, Odhran, for joining us today. We had very fruitful and useful discussion, and I think that safety sometimes is not being discussed as widely as it should be. So I really appreciate to bring those concerns in the attention of like larger community, and looking forward to see all your great work that you do in the future. And thanks everyone for attending and asking good questions.
It's been a pleasure. Bye for now.